Hello there, my friend. Yes, you. The one with the curious eyes and the ever-whirring mind. I see you. Where are you right now? Are you curled up in a comfy chair, the soft glow of a screen illuminating your face? Perhaps you're sitting by a window, the gentle hum of the world outside a familiar lullaby. Maybe you're even outside, under the vast inky canvas of the night sky, a silent witness to the celestial ballet above. Take a moment, pause, look up. Even if you're indoors, close your eyes and imagine it. Picture that sprawling, star-dusted river of light that has captivated humanity for millennia. That celestial masterpiece we call the Milky Way. Our ancestors gave it beautiful names. The ancient Greeks saw Galaxies, Kyklos, the Milky Circle. The Romans, Via Lactea, the road of milk. In the Kalahari Desert, it's the backbone of the night. In Finland, Linnanrata, the path of the birds. Every culture, every soul that has ever looked up in wonder has felt a connection to it. Have you ever truly wondered about it? Not just as a pretty band of light, but as a home. Our home. A sprawling, dynamic, and breathtakingly ancient city of stars, gas, and dust. With our little sun tucked away in one of its spiral arms. A city of at least 100 billion stars, and perhaps as many as 400 billion a day. Think about that for a second. For every single person on Earth right now, there are dozens of stars in our galaxy alone, and planets. Astronomers now believe there are more planets than stars. Trillions of worlds, silent and unseen, orbiting those distant suns. Tonight, my friend, I want to tell you a story. Not just any story, but the grandest of them all. The story of how our cosmic home, the Milky Way, was born. It's a tale that stretches back billions of years, long before the first human ever gazed at the stars. A story of cosmic chaos and exquisite order, of cataclysmic explosions and the gentle birth of stars. It's a story written in the language of gravity, light, and time itself. It's a detective story, too, where the clues are written in the faint, ancient light from the edge of the universe, in the chemical composition of the oldest stars, and in the graceful dance of galaxies. But don't worry, I won't bore you with dry equations and impenetrable jargon. We'll take it slow. We'll journey back to a time when the universe was young, dark, and seething with unimaginable energy. We'll watch as the first sparks of light ignite the cosmic darkness, and we'll witness the patient cosmic dance that brought our galaxy into being. This won't be a rushed highlight reel. It will be a gentle, deliberate unfolding. We have all the time in the world, or rather, all the time of the world. So, get comfortable, settle in, let the noise of your world fade away. For the next little while, you and I are going on an adventure, a journey to the very beginning of everything we know, a journey to the birth of our own cosmic address. Are you ready? Let's begin. Chapter 1, The Cosmic Overture, a universe in its infancy. Before there was a Milky Way, before there was a single star, a planet, or even an atom, there was something else. It's a place our minds can barely grasp, a state of being so alien it defies all our everyday intuition. To start our story, we must travel back, not just in space, but in time. All the way back, our journey starts 13.8 billion years ago. There is no where in the sense we understand it, because space itself is part of what is about to be born. There is no before, because time, too, is waiting in the wings. There is only a point, a singularity, a zone of infinite density and temperature, smaller than a grain of sand, yet containing all the energy, all the matter, all the potential for everything that would ever be. The entire universe, with its billions of galaxies, its septillions of stars, and you, sitting here, reading this, all of it was compressed into this unimaginable state. And then, it happened. The Big Bang. Now, forget the idea of a cosmic firecracker exploding in space. That's a common misconception. The Big Bang wasn't an explosion in space. It was the explosion of space. In an instant, a fraction of a second, so small, it makes a blink of an eye feel like an eternity, the universe began to expand. Not expand into anything, but expand within itself. Space itself started to stretch, carrying the energy and nascent particles along with it. This initial burst was followed by something even more mind-boggling: cosmic inflation. In a fleeting moment, from about 1036 to 1032 seconds after the Big Bang, the universe underwent a period of exponential growth. It ballooned in size, expanding faster than the speed of light. It's as if you took a single marble and in a fraction of a heartbeat, it grew to be larger than the entire observable universe we see today. This inflationary period is crucial to our story. It was like taking a crumpled up sheet of paper and stretching it out until it was almost perfectly flat. It smoothed out the universe, explaining why, on the largest scales, it looks so uniform. But it wasn't perfectly smooth. There were tiny quantum fluctuations, infinitesimal ripples in the fabric of this primordial energy soup. Think of them as tiny imperfections, variations in density no bigger than 1 part in 100,000. During inflation, these microscopic ripples were stretched to colossal astronomical scales. Hold on to that thought. These tiny, almost insignificant ripples are the seeds of everything. They are the future locations of galaxies. One of those ripples, a slightly denser patch in the cosmic fabric, is the very seed of our Milky Way, right there. In the first sliver of a second of existence, the spot where our home would one day be was already faintly sketched into the blueprint of the cosmos. It's a humbling thought, isn't it? Our grand galaxy, a consequence of a quantum burp at the dawn of time. As inflation ended, the universe was still an exotic, seething inferno. It was a quark-gluon plasma, a soup of fundamental particles whizzing about at incredible speeds and energies. It was far too hot for protons and neutrons to form, let alone atoms. The 4 fundamental forces of nature that govern everything today, gravity, electromagnetism, and the strong and weak nuclear forces, were still settling into their distinct identities. The universe continued to expand, and as it expanded, it cooled. It's like letting the air out of a pressurized canister. The expanding gas becomes colder. After about 1 microsecond, it was cool enough for quarks to bind together, forming the first protons and neutrons, the building blocks of atomic nuclei. For the next 3 minutes, the entire universe was like the core of a giant star. In a process called Big Bang nucleosynthesis, the protons and neutrons fused together. The searing heat and immense pressure cooked them into the first atomic nuclei. Mostly, they formed hydrogen, a single proton, and helium, 2 protons, 2 neutrons, with tiny trace amounts of lithium, and that was it. the cosmic oven switched off. The universe became too cool and spread out for further fusion to occur. For all the complexity we see around us today, the carbon in our DNA, the oxygen we breathe, the silicon in the device you're reading this on, the early universe could only manage to cook up the 3 lightest elements. The rest of the periodic table would have to wait for the first stars to be born. Our story is, in essence, the story of how the universe learned to create complexity. So, let's take stock of where we are. We are now a few minutes into the life of the universe. We have a rapidly expanding cosmos filled with a hot, dense, opaque fog of charged particles, protons, helium nuclei, and electrons, and a sea of photons, particles of light. The photons are trapped, constantly scattering off the free-floating electrons, like car headlights in a thick fog. They can't travel far. The universe is glowing, but it is not yet transparent. It is a brilliant, blinding, featureless haze. And, importantly, we have those slightly denser regions, the stretched-out quantum ripples from the inflationary era. These are the regions where there's just a little bit more stuff. This is where our silent and patient protagonist, gravity, begins its work. Chapter 2: The Dark Age and the Invisible Hand. For the next 380,000 years, the universe continued to expand and cool in a state of monotonous, glowing fog. Imagine being inside a cloud so dense you can't see your own hand in front of your face. That was the entire universe. While it might seem like not much was happening, this was a crucial period of quiet preparation. Throughout this glowing soup, our old friend gravity was already at work, but it was fighting an uphill battle. The outward pressure of the photons, the light itself, was immense, trying to push everything apart. It was a cosmic tug-of-war. Gravity tried to pull the matter in the denser regions together, while the radiation pressure pushed it back out. This created vast, slow oscillations, like sound waves sloshing through the primordial plasma. These are called baryon acoustic oscillations, and they left another subtle imprint on the cosmos that we can still detect today. But there was another player in this game, a mysterious and silent partner, one that didn't interact with light at all, one that felt the pull of gravity but was completely immune to the pushing of the photons. We call it dark matter. Let's pause on this, because you can't tell the story of the Milky Way without it. Dark matter is the invisible skeleton of the cosmos. We can't see it, we can't touch it, and it doesn't emit, absorb, or reflect any light. It's completely transparent. So how do we know it's there? We see its effects. We see galaxies spinning so fast they should fly apart, but something's holding them together. We see light from distant objects being bent as it passes through space, distorted by the gravity of something we can't see. This mysterious substance makes up about 27% of the universe. The normal matter, the stuff that makes you and me and stars and planets, is only about 5%. The rest, a whopping 68%, is an even more enigmatic force called dark energy, which is causing the expansion of the universe to accelerate. But for our story of formation, dark matter is the key. Think of it like this. Imagine a giant, invisible spiderweb stretching throughout the entire universe. This web is made of dark matter. Now, imagine spraying a fine mist of water onto it. The water droplets, our normal matter, will be drawn by surface tension to the threads of the web. collecting in the densest intersections. That's exactly what was happening in the early universe. While the normal matter was being pushed and pulled by light, the dark matter, immune to this pressure, was calmly and quietly collapsing under its own gravity. It began to pool in those slightly denser regions we talked about earlier, forming vast, invisible clumps we call halos. These dark matter halos were the gravitational wells, the cosmic potholes, into which normal matter would eventually fall. The seed of the Milky Way wasn't just a ripple of normal matter. It was, more fundamentally, a growing halo of dark matter. Now, back to our timeline. For 380,000 years, the universe expanded and cooled. Eventually, it reached a milestone temperature of about 3,000 degrees Celsius, or 5,400 degrees Fahrenheit. This was cool enough for the frantic electrons to finally slow down and be captured by the waiting protons and helium nuclei. Atoms were born. This event is called recombination, and it changed everything. With the electrons now bound into atoms, the photons were suddenly free. The thick fog that had filled the universe for millennia lifted in an instant. The universe became transparent. The light that was present at that exact moment was finally liberated, free to travel unimpeded across the cosmos forever. Today, 13.8 billion years later, we can still see this light. As the universe has expanded, this light has been stretched. Its wavelength elongated, so it's no longer visible light but exists in the microwave part of the spectrum. This is the cosmic microwave background, CMB. When you see those famous maps of the CMB, those modeled blue and red images, you are looking at a baby picture of the universe. You are seeing the light from that moment of first transparency. And those tiny temperature fluctuations in the map, those red spots that are just 100,000th of a degree warmer, are the imprints of those original density ripples. They are the direct proof of the seeds of cosmic structure. One of those slightly hotter, denser red spots on that map is the birthplace of our galaxy. The liberation of this light marked the beginning of a new era. The universe was now transparent, but it was also dark. There were no stars, there were no galaxies. The brilliant glow of the primordial fireball had faded into an invisible microwave background. The cosmos was filled with vast, silent clouds of hydrogen and helium gas, slowly, inexorably, being drawn into the gravitational embrace of the even vaster, invisible halos of dark matter. This was the cosmic dark age. It would last for hundreds of millions of years. It was a time of quiet anticipation, of immense potential brewing in the cold and the dark. The stage was set. The raw materials were in place. The invisible scaffolding was built. All that was needed was a spark to ignite the darkness. Chapter 3. Let there be light. The first stars. For 200 million years, the universe waited in darkness. It was a vast, silent ocean of neutral hydrogen and helium gas, slowly churning as gravity did its patient work. The dark matter halos continued to grow, their gravitational pull becoming ever stronger. Inside these halos, the normal matter, the hydrogen and helium gas, began to accumulate like water vapor condensing into a cloud. Imagine one of these clouds. It's hundreds of thousands of times the mass of our sun, but it's incredibly diffuse, spread out over a vast region of space. As gravity pulls it inward, the cloud begins to collapse, under its own weight. The gas particles rub against each other, creating friction and heat. But unlike clouds today, this primordial gas had a problem. It was terrible at cooling down to collapse and form a star. A gas cloud needs to radiate away its heat. If it can't, the internal pressure from the heat will push back against gravity, halting the collapse. Today, gas clouds are enriched with heavier elements like carbon and oxygen. These elements act like tiny, efficient radiators, allowing the cloud to cool effectively and fragment into thousands of smaller clumps, each forming a star like our sun. But this first-generation gas had no carbon or oxygen. It was pure hydrogen and helium, the simple leftovers from the Big Bang. These elements are very inefficient at radiating heat. The only way the cloud could cool was through the much clunkier process of molecular hydrogen H2 formation. This meant the cloud couldn't easily fragment. It just kept collapsing as one enormous, monolithic entity. The core of this collapsing giant cloud grew denser and hotter. The pressure became unimaginable. Finally, after millions of years of slow contraction, the core reached a temperature of about 10 million degrees Celsius. At this point, a miracle happened. The protons, the nuclei of the hydrogen atoms, which had been furiously repelling each other, were slammed together with such force that they fused. Ignition. In the heart of the primordial darkness, the first star blazed into existence. But this was no ordinary star. This was a population 3 star, as we call them, a true cosmic monster, formed from that pristine, metal-poor gas. These stars were colossal. We estimate they were hundreds, perhaps even 1,000 times more massive than our Sun. And because of their immense mass, they were breathtakingly luminous and incredibly hot. Their surface temperatures were scorching, many times hotter than the Sun's, causing them to shine with a brilliant blue-white light. Imagine the scene. After 200 million years of absolute blackness, the first of these titans flickered to life, and then another, and another, scattered throughout the infant universe. They were like cosmic lighthouses, their fierce ultraviolet radiation blasting out into the surrounding darkness. This first light began to end the cosmic dark age. Their radiation was so intense, it ripped the electrons off the surrounding neutral hydrogen atoms, a process called reionization. The universe was starting to transition from a neutral, dark state back into an ionized plasma, but this time it was punctuated by the brilliant points of starlight. These population 3 stars lived fast and died young. A star's lifespan is determined by its mass. The more massive it is, the faster it burns through its fuel. Our Sun will live for about 10 billion years. These behemoths, with their hundreds of solar masses, burned through their entire supply of hydrogen in just a few million years, a cosmic blink of an eye. But in their short, spectacular lives, they performed an act of cosmic alchemy that would change the universe forever. In their cores, they fused hydrogen into helium. When the hydrogen ran out, they began fusing helium into heavier elements. For the very first time, the universe saw the creation of carbon, oxygen, nitrogen, and all the elements essential for life. The universe was learning to cook when these massive stars reached the end of their short lives. They didn't fade away quietly. They went out with a bang, a very, very big bang. They exploded as magnificent supernova cataclysms of such violence. They could temporarily outshine all the other stars in their vicinity combined. These explosions were the universe's first great dispersal events. They blasted the newly forged heavy elements out into space, seeding the surrounding pristine gas clouds with this precious new material. Carbon, oxygen, silicon, iron, the very building blocks of planets and people were scattered like celestial pollen into the interstellar medium. Think about the iron in your blood, the calcium in your bones, the oxygen you are breathing right now. Where did it come from? It was forged in the fiery heart of a star that lived and died long before our Earth even existed. Most likely, it was created inside one of these first-generation monster stars. You are, quite literally, made of ancient stardust. You are a direct descendant of these first cosmic titans. The death of these first stars was not an end, but a beginning. Their supernova shockwaves ripped through the nearby gas clouds, compressing them and triggering a new wave of star formation. But this second generation of stars, which we call Population 2, would be different. They were forming from gas that was now polluted or enriched with the heavy elements from their predecessors. This enrichment had a profound effect. The presence of carbon and oxygen allowed these new gas clouds to cool much more efficiently. This meant they could fragment into smaller clumps. Instead of forming one single monster star, a cloud could now give birth to a whole cluster of smaller stars. Stars that were still large by today's standards, but much less extreme than the Population 3 giants. Some of these would be a few times the mass of the Sun, others perhaps tens of times. And so a cycle began. Stars were born, they forged new elements, they died, and they enriched the next generation. Each cycle added more heavy elements to the cosmic mix. The universe was becoming more chemically complex, more capable, more interesting. And it was in this flurry of early star birth and death that the first building blocks of our galaxy started to come together. These weren't galaxies yet, not in the grand sense we think of them. They were small, scrappy collections of stars and gas, what we call protogalaxies or dwarf galaxies. They were the first villages in what would eventually become the sprawling metropolis of the Milky Way. Our home was starting to take shape, one starburst at a time. Chapter 4: The Cosmic Web and the Rise of Villages, with the first stars born and dying. The universe was now a very different place. It was no longer uniformly dark. It was a tapestry of light and shadow, with brilliant knots of star formation separated by vast gulfs of cold, dark space. The process of reionization was in full swing, with the bubbles of ionized gas around the first stars and protogalaxies expanding and merging, gradually clearing the cosmic fog for good. Now, let's zoom out. Let's look at the universe on the largest possible scales. Remember our invisible scaffolding of dark matter, those vast halos that were pulling in the gas. These halos weren't distributed randomly. They were arranged in a magnificent, intricate structure known as the cosmic web. Imagine a three-dimensional network. It has vast, almost empty regions we call voids. It has long, thin strands or filaments connecting everything. And where these filaments intersect, you find dense, massive clumps or nodes. The dark matter, and therefore the normal matter, was arranged in this cosmic lacework. The voids were the great cosmic deserts. The filaments were the interstellar highways. And the nodes were the bustling intersections where the action was happening. It was within the filaments, and especially at the nodes of this web, that the first protogalaxies were forming. These were the tiny star systems we mentioned, the villages of the cosmos. They were a chaotic, messy bunch, not the elegant spiral structures we see today. They were clumpy, irregular, and undergoing furious bursts of star formation, fueled by a steady stream of cold gas flowing in along the cosmic filaments. Think of it like a network of rivers and streams. The gas flowed along the filaments like water, and where the streams met, they formed turbulent, churning pools. These pools were the protogalaxies. Inside them, the cycle of star birth and death was proceeding at a frantic pace. Supernova from massive stars blasted enriched gas outwards, but the gravitational pull of the protogalaxies' dark matter halo was strong enough to hold onto much of it, recycling it into new generations of stars. Our own Milky Way didn't just pop into existence as a grand spiral. It was built piece by piece over billions of years through the collision and merging of these smaller protogalaxies. This is the heart of our story. The Milky Way is an immigrant nation, built by the coming together of dozens, perhaps hundreds, of smaller cosmic communities. This process is called hierarchical formation. Small things form first, and then they merge to form bigger things. Let's picture the scene. Around 12 to 13 billion years ago, in our particular corner of the universe, within a particularly dense node of the cosmic web, a dozen or so of these proto-galaxies are starting to feel each other's gravitational influence. They are on a cosmic dance floor, slowly circling each other, getting closer with each pass. These proto-galaxies are not all the same. Some are larger, containing a few million stars. Others are smaller, little more than glorified star clusters. They each have their own history, their own unique mix of stars and gas, their own dark matter halo. Among them is one that is, perhaps, just a little bit more massive than the others. It has a slightly larger dark matter halo, giving it a gravitational advantage. Let's call this one the Proto-Milky Way. It's not our galaxy yet, but it's the dominant player in this local group, the gravitational anchor around which the drama will unfold. Gravity is a patient but relentless force. Over millions of years, the dance of these proto-galaxies becomes more intimate. They begin to stretch and distort each other. Streams of stars and gas are pulled out from the smaller systems by the gravitational tides of the larger ones, creating beautiful, ephemeral arcs of light across the dark space between them. We call these tidal streams. Then, the first collisions happen. These aren't like car crashes. Space is mostly empty, so individual stars rarely, if ever, hit each other. Instead, it's a merger of gravitational fields. As a smaller dwarf galaxy plunges into the Proto-Milky Way, it's a process of gravitational friction and disruption. The dwarf galaxy's stars are stripped away and scattered, adding to the growing stellar population of the larger system. Its gas clouds are compressed, triggering a fresh, violent burst of star formation. Its dark matter halo merges with the larger halo, adding to its mass and gravitational dominance. This was galactic cannibalism. The Proto-Milky Way grew by eating its neighbors. With each merger, the Proto-Milky Way became larger, more massive, and its gravitational reach extended further. Each devoured dwarf galaxy left its mark. Its stars, with their unique chemical fingerprints, and orbital paths became part of the larger whole, but they didn't just mix in perfectly. Many of them were flung out into wide, looping, eccentric orbits, forming a vast, diffused sphere of stars around the central region. This sphere is what we now call the stellar halo of the Milky Way. It's the oldest and most ghostly component of our galaxy. The stars in the halo are ancient. They are population 2 stars, born in those early dwarf galaxies. They are metal-poor, meaning they have a much lower concentration of heavy elements compared to stars like our Sun. They are the living fossils of the galaxies that were consumed to build our own. When we look at the Milky Way's halo today, we can still see the evidence of this ancient feast. We find distinct stellar streams, like the Sagittarius stream, which are the shredded remains of a dwarf galaxy currently being torn apart and absorbed by the Milky Way. By studying the orbits and chemistry of halo stars, astronomers can act like cosmic archaeologists, reconstructing the family tree of our galaxy and identifying the different building blocks that went into its construction. It's like finding the ruins of ancient villages scattered around the outskirts of a modern megacity, telling the story of its origins. So, for 1 billion or 2 years, this was the primary way our galaxy grew. A chaotic, violent, and messy period of constant mergers and acquisitions. The Proto-Milky Way was slowly assembling its outer halo, becoming a more substantial and formidable presence in its cosmic neighborhood. But the iconic, beautiful spiral disk, the part we usually think of as the Milky Way, had yet to form, that required a different kind of evolution, a settling down after the chaotic frenzy of youth. Chapter 5: The Great Collision and the Birth of the Disk. Our galaxy's childhood was a tumultuous one, defined by the relentless pull of gravity and the dramatic consumption of its smaller neighbors. By about 10 billion years ago, the Proto-Milky Way had grown substantially. It had a large dark matter halo and a sprawling, puffy collection of old metal-poor stars, its stellar halo. But it was still a far cry from the majestic spiral we know today. It was more of a disorganized, chaotic ball of stars. The era of massive, frequent mergers was beginning to slow down. The biggest players in the local cosmic neighborhood had cleared out most of the smaller competition. But there was one more big event to come. A collision so significant that it would fundamentally reshape our young galaxy and set the stage for the birth of the Sun. Modern astronomical detectives, using data from powerful telescopes like the Gaia Space Observatory, have uncovered compelling evidence for this transformative event. They have found a distinct population of stars in the Milky Way's inner halo that are all moving in a peculiar way. They are on highly elongated, sausage-shaped orbits, plunging in and out of the galactic center. By tracing back their motions, astronomers have deduced that these stars are the debris of a single massive dwarf galaxy that collided with our own. They've nicknamed this galaxy Gaius Enceladus, GSE, Gaia for the telescope that found it, sausage for the shape of the star's orbits, and Enceladus from Greek mythology, a giant who was buried under a mountain. This was no small snack. The GSE was a hefty galaxy in its own right, perhaps about 1/10 of the mass of the Proto-Milky Way at the time. Its collision was not just another minor merger. It was a defining moment in our galaxy's life. Let's try to visualize it. 10 billion years ago, the young Milky Way is tumbling through space, a vaguely spherical cloud of stars and gas approaching. It is the GSE galaxy, a brilliant swarm of millions of stars on a collision course. The gravitational dance begins. As they draw closer, tidal forces stretch both galaxies. A bridge of stars and gas forms between them. Then the impact. The GSE plunges head-on into the heart of the Proto-Milky Way again. Individual stars don't crash, but the two systems interpenetrate. The gravitational shock is immense. The GSE is torn to shreds. Its stars are scattered like shrapnel from an explosion, thrown onto those characteristic, long, looping sausage orbits that we still see today. These stars now make up a significant portion of our galaxy's inner halo. But the effect on the Proto-Milky Way was just as profound. This was a messy, chaotic event. The gas clouds from both galaxies slammed into each other, compressing the gas and triggering an absolutely colossal burst of star formation. A starburst on a galactic scale. For a time, our galaxy would have blazed with the light of millions of newborn, massive blue stars. Most importantly, this collision marked the end of our galaxy's violent youth and the beginning of its adolescence. The immense gravitational churning from the merger had a settling effect on the gas within the newly combined system. All that gas, which had been sloshing around chaotically, was now subject to a more ordered gravitational field. And this is where a fundamental law of physics comes into play: the conservation of angular momentum. Think of an ice skater spinning. When her arms are outstretched, she spins slowly. When she pulls her arms in, she spins faster. The total amount of her spin, her angular momentum, stays the same. The gas cloud that formed the combined Milky Way SE system had some initial, random net rotation. It wasn't spinning perfectly, but there was an overall average spin in one direction. As the gas cooled and lost energy from the chaotic collision, it couldn't just fall straight into the center because of this spin. Instead, it began to settle and flatten out, just like that ice skater pulling in her arms. Over hundreds of millions of years, the messy, turbulent, three-dimensional cloud of gas collapsed down into a thin, dense, rapidly rotating disk. This was the birth of the Milky Way's disk. This newly formed disk was a fertile breeding ground for stars. It was dense with gas, now significantly enriched with heavy elements from the generations of stars that had lived and died in both the Proto-Milky Way and the GSE. The conditions were perfect for ongoing sustained star formation, very different from the frantic, short-lived starbursts of the past. The stars born within this disk were different from the ancient halo stars. These were population I stars, like our Sun. They were born from enriched gas, so they are metal-rich. And because they were born from a rotating disk, they inherit its motion. They all travel on neat, orderly, circular orbits around the galactic center, all moving in the same direction, like cars on a multi-lane highway. This is why the Milky Way has its distinct components. The halo, a vast, spherical cloud of ancient metal-poor stars on random, eccentric orbits. These are the fossils of the dwarf galaxies that our Milky Way consumed in its youth, including the prominent debris from the Gaia-Sausage-Enceladus merger. The disk, a thin, flat, rotating plane containing gas, dust, and younger metal-rich stars, like our Sun, all on orderly circular orbits. This is where the ongoing star formation happens. The central bulge, a dense, football-shaped region of mostly older stars, at the very center. It's a bit of a mix, likely formed from a combination of the earliest starbursts and the disruptive effects of the galactic bar that would form later. And within that disk, another beautiful structure began to emerge. The disk wasn't perfectly uniform. Tiny density variations, amplified by the gravity of the stars and gas themselves, began to form elegant, sweeping patterns. These are the spiral arms. The spiral arms are not solid structures. You might think of them as cosmic traffic jams. They are density waves, regions where the gas and dust are slightly more compressed. As gas clouds move into a spiral arm, they get squeezed. This compression is enough to trigger the collapse of the clouds and the birth of new stars. This is why the spiral arms are so bright and prominent. They are lined with brilliant, young, massive blue stars. These stars are so luminous they light up the whole arm, but they are also short-lived. They are born in the arm, shine brightly, and then die, often before they have a chance to move out of the arm. The longer-lived, yellower stars, like our Sun, however, pass right through the spiral arms like cars passing through a temporary slowdown on the highway. So, by about 9 billion years ago, our Milky Way was beginning to look like the galaxy we know, a luminous central bulge, a vast rotating disk with emerging spiral arms, all surrounded by a ghostly halo of ancient stars. It had survived a violent childhood, settled into a more graceful adolescence, and was now a mature, star-forming galaxy. The stage was finally set for the birth of a very particular, rather unremarkable yellow star in a quiet suburb of one of those spiral arms. Chapter 6. A star is born, our Sun's quiet arrival for billions of years after the formation of the disk. The Milky Way continued its stately, quiet evolution. It wasn't completely peaceful. It still snacked on the occasional small dwarf galaxy, like the Sagittarius dwarf we see it consuming today. But the era of cataclysmic, transformative mergers was over. The main event was the steady, ongoing process of turning gas into stars within the grand spiral disk. Our story now zooms in, way in. From the scale of the entire galaxy, we now focus on a single, unremarkable region within one of its spiral arms, what we now call the Orion Cygnus arm. The time is roughly 4.6 billion years ago. The universe is already over 9 billion years old. Our galaxy is mature and stable. The location is a vast, cold, dark cloud of gas and dust. We call such a cloud a giant molecular cloud. It's a stellar nursery. It's immense, spanning dozens of light years, and it's cold, just a few tens of degrees above absolute zero. Its darkness comes from the tiny grains of dust silicates and carbon compounds, the soot from previous generations of stars which blocked the light from the stars behind it. This cloud is composed mostly of hydrogen and helium, but it's also richly seasoned with all the heavier elements forged in stars over the preceding eon. It has carbon, oxygen, nitrogen, iron, gold. Everything in the periodic table is floating around in this cold, dark brew. For a long time, this cloud is stable. Its internal gas pressure and slight magnetic fields balance out the inward pull of its own gravity. But then, something gives it a push. Perhaps it's the shock wave from a nearby supernova, the death of a massive star just a few light years away. Or maybe it's the gentle but persistent compression as the cloud passes through one of the galaxy's spiral arms. Whatever the trigger, a region within the cloud begins to collapse. Gravity takes over. A clump of material, a few light years across, starts to contract, pulling in more and more gas and dust from its surroundings. This collapsing core is our solar nebula. As the nebula shrinks, two things happen, just as they did for the galaxy's disk, but on a much smaller scale. First, it heats up. The gravitational potential energy of the falling material is converted into thermal energy. The center of the nebula becomes a hot, dense protostar. Second, due to the conservation of angular momentum, it begins to spin faster and flatten into a disk. We now have a spinning, flattened disk of gas and dust, about the size of our solar system, with a glowing, hot protostar at its center. This is the protoplanetary disk. It's the birthplace of not just our sun, but of Earth and all the other planets. For about 100,000 years, the central protostar continues to grow, accreting more material from the disk, getting hotter and denser. Its own nascent solar wind radiation begin to push back against the inflow of material. Eventually, the pressure and temperature in its core reach the magic number. About 15 million degrees Celsius, nuclear fusion ignites. Our sun is born. It switches on, a brilliant young star, and its light illuminates the swirling disk of gas and dust surrounding it. It wasn't quite the calm, steady sun we know today. It was likely a more tempestuous, active young star, with violent flares and a much stronger solar wind. But what about the disk? What about the leftover material that didn't fall into the sun? This is where the planets come from. The process of planet formation began even as the sun was still a protostar. Think of the protoplanetary disk as a dusty, gaseous ring, close to the hot young sun. It was too warm for volatile materials like water, ammonia, and methane to condense into ice. Only rocky materials and metals could solidify. So, tiny grains of dust, silicates, and iron began to stick together at first. It was electrostatic forces, like dust bunnies, forming under your bed. Specks of dust clumped into slightly larger aggregates. As they grew, their own gravity started to help. They grew from dust grains to pebbles, from pebbles to boulders, from boulders to planetesimals, objects a few kilometers across. This was a chaotic and violent time in the early solar system. These planetesimals, millions of them, were all orbiting the young sun. They collided constantly. Sometimes the collisions were destructive, shattering them back into smaller pieces. But sometimes they were gentle enough that the two objects merged, a process called accretion, over millions of years. The largest planetesimals grew the fastest, their stronger gravity sweeping up all the smaller debris in their orbital path. It was a case of the rich getting richer. Eventually, in the inner solar system, 4 large bodies emerged from this collisional free-for-all. These became the rocky, terrestrial planets: Mercury, Venus, Earth, and Mars. The formation of our own Earth was a particularly dramatic story. It likely involved a massive collision with a Mars-esque planetesimal named Theia. This cataclysmic impact would have melted the young Earth, and the debris thrown out from the collision eventually coalesced to form our moon. Further out in the disk, beyond a boundary we call the frost line, it was much colder. Here, it was cold enough for water, methane, and ammonia to freeze into solid ice. This meant there was much more solid material available to build planets. So, in this outer region, massive cores of rock and ice were able to form 10 times the mass of the Earth. These giant cores became so massive that their gravity was strong enough to pull in and hold onto the vast amounts of hydrogen and helium gas left over in the nebula. They rapidly swelled into colossal gas giants. This is how Jupiter and Saturn were born. Uranus and Neptune, the ice giants, formed a bit later and further out where there was less gas, so they ended up with smaller gaseous envelopes around their icy core. After about 10 to 100 million years, the process was largely complete. The young sun's powerful solar wind and radiation had blown away most of the remaining gas and dust from the disk, ending the era of planet formation. What was left was the solar system we know today, a stable yellow star at the center, for rocky planets in the inner regions, 2 gas giants and 2 ice giants in the outer realms, and the leftover debris, the asteroids in the asteroid belt, the comets in the Kuiper belt, and the distant Oort cloud. Our solar system was born, a tiny, precious, and intricate system nestled in the suburbs of a vast, ancient city of stars. Our Earth was a hot, volcanic, and lifeless world at this point, but it had an orbit, it had a moon, and it had all the necessary chemical ingredients, delivered by comets and asteroids. For the next chapter of the story to begin, the origin of life, our cosmic home, the Milky Way, had spent billions of years assembling itself from the chaos of the Big Bang. It had built its halo from cannibalized galaxies, forged its disk in a great collision, and ignited its spiral arms with generations of stars. All of that cosmic history, all of that patient work by gravity and time, led to the creation of a stable, nurturing environment where a small cloud could collapse, a star could ignite, and a little blue planet could form. Chapter 7. Our place in the grand river of Nighttand. So, here we are, on a small, rocky planet, orbiting a middle-aged star in a quiet neighborhood of a very large galaxy. We've journeyed back 13.8 billion years, from the singular moment of creation to the formation of our solar system. We've seen how the grand, sweeping narrative of the cosmos led, step by patient step, to our own existence. But the story of the Milky Way isn't over. It's still evolving, still changing, still dancing to the silent music of gravity. Our sun and its planets continue their long, slow journey around the galactic center, completing one full orbit every 230 million years or so. This is a galactic year. The last time we were in this position in the galaxy, dinosaurs roamed the Earth since its birth. Our sun has made this trip about 20 times. Our galaxy continues its quiet cannibalism. The Sagittarius dwarf galaxy is being shredded as we speak, its stars being woven into the fabric of the Milky Way's halo. Other smaller satellite galaxies, like the large and small Magellanic Clouds, visible from the southern hemisphere, are our companions for now, but in a few billion years, they too will likely be consumed, their stars and gas merging with our own. And there is another, much larger collision on the horizon. The Andromeda Galaxy, our nearest large spiral neighbor, is hurtling towards us at a speed of about 110 kilometers per second. There's no need to panic. It's still 2.5 million light-years away, but the collision is inevitable. In about 4.5 billion years, the Milky Way and Andromeda will meet. It will be a spectacular, graceful, and drawn-out event, lasting for hundreds of millions of years. As the two galaxies plunge through each other, vast tidal tails of stars and gas will be flung out into intergalactic space. The gas clouds within both galaxies will be compressed, triggering a magnificent starburst that will light up the merging system. Eventually, after several passes, the two spiral galaxies will settle and merge into one single, giant elliptical galaxy. Our solar system will almost certainly survive, unscathed, thrown into a new, wider orbit within this new, larger galaxy, which some have nicknamed Milky Way. The night sky for any future inhabitants of Earth will be breathtakingly different, filled with the brilliant light of countless newborn stars. That is the distant future of our home. But for now, let's come back to the present, to tonight. When you go outside and look up at that faint, shimmering band of light, you are not just seeing a random collection of stars. You are looking into the heart of our own story. You are seeing the light from stars in the disk of our galaxy. The dark lanes that seem to cut through the Milky Way are the giant molecular clouds, the stellar nurseries, just like the one our sun was born in, waiting for the right push to create the next generation of stars and planets. When you look towards the constellation Sagittarius, you are looking towards the dense, bright central bulge of our galaxy, towards the supermassive black hole, Sagittarius A*, that sits at its very heart, a silent, gravitational anchor around which our entire city of stars revolves. When astronomers study the ancient faint stars in the halo, they are reading the fossil record of our galaxy's violent birth, uncovering the ghosts of long-dead galaxies that sacrificed themselves to build our home. The story of how the Milky Way was born is our story. The iron in the hemoglobin that carries oxygen through your veins was forged in a supernova explosion that seeded the cloud that formed our sun. The carbon that forms the backbone of your DNA was created in the core of a star that died billions of years ago. The water in your body is made of hydrogen forged in the Big Bang itself. You are not separate from the universe. You are a part of it. You are a way for the cosmos to know itself. All the eons of cosmic evolution, the formation of particles, the birth and death of stars, the collision of galaxies, all of it has conspired to create this moment, right here, right now, where a piece of the universe can sit and contemplate the whole. So, the next time you find yourself under a clear, dark sky, take a moment, find that milky path of light, and remember the incredible journey it has taken. Remember the primordial fireball, the cosmic dark age, the monstrous first stars, the violent collisions, and the patient settling of the disk. Remember the story of your cosmic home, a story of chaos and creation, of violence and beauty, of dust and destiny, a story that is still being written across the vast, silent canvas of the night. And you, my friend, are a part of it.